So now we will understand the relationship between K, that is the equilibrium constant, Q, that is the reaction quotient, which tells you the direction of the reaction, and delta G, which is the Gibbs energy change. Okay, so Kc value, as we know, it does not depend on the rate of a reaction. Okay, it does not depend on the rate of a reaction. What do you mean by that? It does not matter how fast or how slow the reaction is happening, or how fast the equilibrium has attained. Okay, the it is constant at a given temperature. It is independent of the. Now, if I have to tell this, Kc is independent of the initial concentration. It is independent of the rate of the reaction. So it doesn't matter how fast the reaction is happening. Maybe you're adding a catalyst which might increase or decrease. The value of Kc will still be the same. Maybe initially you started with 10 moles maybe of some two reactants, and you got Kc as 100, for example. Later you added and in the second set maybe you started with 50 moles. Okay, the Kc value in this case after it attained equilibrium will still be the same. Why? Because Kc is the concentration of product by reactants. Let us say this ratio was 100 initially. For example, if it was 100, and let us say this was like 1000 and this was 10. Just I'm giving some value. Okay. Now in the second set of experiments, instead of taking 10 moles of react, now this is the moles with which you have started. Okay, so let us say initially you started with I'm just taking some example. Okay, 50 moles, for example, 50 moles of the reactant. This is the 50 moles of the reactant. Okay, you started with 50 moles of the reactant initially. 40 moles got consumed, 10 moles were remaining during equilibrium, and we were getting 1000 moles of the product, for example. Okay, so that means equilibrium constant here is going to be 100. Now, even if you had started with, instead of 50, let us say you started with 500 moles of reactants. Okay, even in this case, this value is going to be the same, because if you start with the greater value, you will have a greater value here. Let us say 50 is becoming 10 times, right? So this will also be 10 times, and this will also be 10 times. If you see the net, the Kc is constant. So what do you mean? Initially, it doesn't depend on initial concentration. It only depends on the concentration at that equilibrium state. What are the values of this? So even if you're changing the initial concentration of the reactants, what is happening if it's increased? The concentration of the reactants when the equilibrium was achieved is also changing by the same extent, so that Kc remains constant. Okay, so it does not depend on the rate of a reaction, it does not depend on the initial concentration, it only depends on thermodynamics. That is delta G, which is the Gibbs free energy available for a reaction to happen. Okay, and you know this, if delta G is negative, we have studied this, it is spontaneous. Delta G is positive, it is non-spontaneous in the forward direction, because assuming that this is a delta is negative, when we say, it's obviously spontaneous in the forward direction and spontaneous in the backward direction. So if G is negative, it is spontaneous in which direction? Forward. And positive, non-spontaneous forward, and spontaneous in the backward. And if delta G is 0, what do you mean by that? There is no free energy left for reaction. That means it is in equilibrium. Okay, if there is nothing energy, that means reaction cannot happen. That means it has already achieved a state of equilibrium. Okay, so the why this is happening, okay, why this condition is happening, we have already studied it from the thermodynamics perspective. Let us now understand this. Why is this happening? Why do we say that when delta G is negative, it is going to be a spontaneous reaction? This explanation we are going to understand now. Alright, so you have free energy change in terms of standard free energy plus RT ln Q. Okay, now this This is something which, if it was delta H, remember it was K here. We had derived it in thermodynamics. But here we have it in RT, L and Q. Okay, now this reaction derivation you don't have, you just have to know. Now, what I'm interested in is this. What is this delta G naught? G this minus of G naught we say. That is the standard condition. So it is the standard free energy change. That means what is standard free energy change? When the conditions are 1 bar pressure and 298 Kelvin. Okay, at this temperature and pressure, whatever is the free energy change which is happening, that is what we call as delta G naught. Okay, now if you take a system at equilibrium, you know this is 0. I have written it. So this becomes 0 is equal to delta G naught plus RT ln Q. Okay, or in other words, I can write delta G naught as negative RT ln Q, or if I have to continue this, it will be ln Q will be equal to delta G naught divided by RT. And if you take anti-log on both sides, you will get Q is equal to e power minus what is this? Minus delta G naught divided by RT. Okay, it is e power this much. This is e power minus delta G naught divided by RT. This is what I get. Okay, now if I consider delta G is negative, we know it is spontaneous, but how? Let us see. Whenever delta G is negative, this value is negative, so what you will get, Q is equal to e power negative of some negative value. This negative is already there, delta G is negative here. So it is nothing but e power positive. And e power positive, E1, E2 is always going to be a number wherein it is greater than 1. Alright, so it is going to be a number which is greater than 1. Okay, just a second. Alright, so I just missed one thing here. At equilibrium, you know QC and KC are same. So I can even replace this Q by KC. Because we are talking about KC here, I can even tell this to be K here. This is only when it is at equilibrium. Remember we said it is 0 here. Delta G is 0 at equilibrium. My Q will be equal to KC. Okay, because QC and KC are same at equilibrium. What is QC? Concentration at anything. And when the time is at equilibrium, QC and KC are the same. So that is when I can write it as K is equal to E power here. Yes. So that means K is greater than 1 here. Correct? K is a E power positive value. K is greater than 1. What do you mean by that? It is just telling you that the concentration of the product is greater than 1. I mean, the concentration of the products is greater. That means it wants to form more and more products, or in other words, it means it is spontaneous. If this is positive, you know, K, if this E power positive number means K greater than 1, and if K greater than 1, it means product concentration is higher. That means more and more products are forming, or in other words, the reaction is spontaneous. And in the other case, when delta G is negative, that is how minus G is spontaneous. We did not study why it is in thermodynamics because we never knew this is the logic for that. Now we are understanding with this base, we are understanding why whenever delta G is negative, why is it spontaneous. Okay, so in this case what happens, K will be E power, K will be equal to E power negative into positive, which is negative. E power negative means it is a number which is less than 1. Right, if you have 2 power 2, it is greater than 1. 2 power minus 2, it is less than 1 because you get 1 by something. And in this case, it implies that product concentration is lesser. If you say product concentration is lesser, that means it doesn't want to form products. Or in other case, it is non-spontaneous. Alright, so this is the explanation in terms of equilibrium constants. The explanation why whenever we say Gibbs free energy change is negative, why do we say that it is spontaneous, or when it is positive, why do we say that it is non-spontaneous in the forward direction. Okay, so of course, if it is non-spontaneous in the forward direction, it will be spontaneous in the backward direction. We know this. That's why I don't want to confuse you. I'm just telling the both conditions only with respect to the forward direction. Okay, now let us take one example. This is 7.10 solved example. Okay, so they have given delta G naught for phosphorylation of glucose. Okay, there is some reaction. Delta G naught is given as 13.8 kilojoules per mole. Okay, this reaction is phosphorylation of glucose to glucose. Basically, conversion of glucose to glucose, and this is given to you. All right, glycolysis it is breakdown of glucose. Yes, you have to find the value of Kc at 298 Kelvin. Okay, so how do we use this? This is given to you in kilojoules. So this is in Kelvin. So your answer should be in joules. So let us, Kc is what? The constant when equilibrium is achieved. So we know that delta G naught is negative RT ln K at equilibrium. So what do we want? We want Kc. So let us write ln K is delta G naught negative divided by RT. Okay, and let us now substitute this. This is going to be minus 13.8 kilojoules. So into 10 power 3 to convert it into joules, and R is 8.3 in SI units into temperature is 298. Alright, if you get this, the answer, if you substitute this, if you calculate this, you will be getting something like this. And what will be Kc? This is log, you just take anti-log, you will get the value of Kc to be 3.81 into 10 power minus 3. Alright, this is how you calculate the value of Kc. Alright, now what and all did we discuss? We discussed the applications, we discussed the concept of Gibbs free energy, how the value of Gibbs free energy tells us whether it is spontaneous or not in one direction. The explanation we have studied, and we have done one numerical. Now, let us also understand the factors affecting equilibrium. Okay, now this is a very elaborate topic. We'll be doing it in parts. I'm just going to do the intro here. Okay, factors affecting equilibrium. Alright, now I'm just going to do the introduction here. So, whenever you say there is a reaction which has, now before even I write something, let me explain you this. You remember the very example where there was a rope and I was trying to walk on the rope like this and carefully, and I achieved a kind of equilibrium. I was able to balance it. But let us say somebody is shaking the rope from there. Okay, so that means there is a disturbance. So I will now, what I will do, I will try to handle the stress. I will try to balance myself in such a way that I need to counteract the stress which is causing the disturbance. Okay, or which is causing the equilibrium to change. Now my equilibrium has been disturbed. I was in a state of equilibrium, but somebody was trying to push the rope from the bottom or from some other direction. So my equilibrium got affected. And then what I do, I try to set up a new kind of equilibrium by readjusting my body, by readjusting my weight, by making sure I do something. Anyways, let's not go into the physics behind that. But yes, so basically what I want to say is, let us say there is a reaction which was in equilibrium or which was trying to achieve equilibrium. It doesn't matter, already achieved or trying to achieve. Okay, and then there is some kind of disturbance. Now in reactions, how can the disturbance be there? Let us understand. It is in the form like you add some reactant, you remove some reactant, you add product, you remove product, something like that. That is what I call as a disturbance. But anyways, disturbance is there which is trying to hinder the equilibrium. Okay, then what happens? The system will make adjustments to counteract the disturbance. System will adjust itself to counteract the disturbance and then set a new equilibrium. You just remember that rope example, it will be very, very clear to you. So if there is a disturbance in the form of addition or removal of product or reactant, then the system will automatically adjust to counteract this disturbance and then set up a new equilibrium. Okay, new equilibrium state. And industrially, the reason why we are studying it is industrially, any yield should be higher. We always need to get higher and higher products. That's the purpose, correct? But let us say equilibrium is achieved at a much earlier state. Then what we need to do? We do not want it, because if equilibrium is at achieved at a earlier stage, it means that the concentration of the product is going to be the same. Whenever we say something is in equilibrium, the concentration of the reactant and products are constant. They are not going to change. Now if the product is concentration is constant, it means that no more product is being formed, or in other words, whatever is being formed, it is converted back into reactants. That is when I say the concentration of the product is constant. And do we want that? We wanted maximum yield, but we have got the reaction is almost stopped, or it appeared to be stopped at the state of equilibrium. Now if I know the factors affecting, I can tweak the factors in such a way that I want the reaction to proceed in the forward direction, so that I get more products. So that's the reason we are trying to study these factors. Okay, and before we study these factors, okay, first let me write the list of all factors. You have 5 factors to be studied here. One by one we are gonna do here in the next videos. The first one is the effect of concentration change. What happens if you increase the concentration or decrease the concentration of a reactant and product? Second one is effect of pressure change. What happens if you increase or decrease the pressure in the reaction, in the equilibrium mixture? Okay, third one is effect of addition of an inert gas. Okay, inert gas is not actually affecting, but let us understand this in detail. The effect of temperature change, alright, and effect of a catalyst. These are the 5 factors which are affecting the equilibrium. Okay, so before I go to each of this, I think it makes much sense for me to tell you about a principle which is called as Le-Chatelet's principle. Okay, so we'll discuss this principle and I'll end the video. In the coming videos, maybe we can cover up the effects of concentration one by one, concentration, pressure, and so on. So Le-Chatelet's principle. This can be asked for 1 mark. State Le-Chatelet's principle. Okay, so what it says is change in any of the factors that determine the equilibrium condition. Any of the factors that determine the equilibrium condition of a system will cause the system to change in a manner to counteract that effect, to counteract that change, like I told you. Okay, or in case of a physical balance also, you can think the equilibrium is now balanced, but what if you put more weights like this? It will turn like this. Again, if you want it to be again you want the system to be brought back to equilibrium, I have to put weight on this side, correct? So exactly the same thing is written in a statement. If there is a change in any one of the factors, we have studied the 5 factors, any one factors, if there is a change which is causing the system, what happens, if there is a change in any one of the factors that determines the equilibrium, then it will cause the system to change. You can write like this. It will cause the system to change in a manner to counteract that change. So the equilibrium was established, there is some disturbance, the system will automatically try to counteract the disturbance and then establish a new equilibrium. Whatever I have just explained, it is put as a statement and it was given by Le-Chatelet. Okay, so in the next videos, we are going to understand the effect of concentration, the effect of pressure, effect of addition of inert gas, temperature and catalyst. Yes.